Russia may have just quietly solved one of the biggest manufacturing problems standing in the way of the PD-14 engine. Not the engine's thrust output, not its fuel efficiency numbers. Something much more basic than either of those, how to actually build it. The PD-14 is supposed to give Russia's MC-21 airliner something genuinely critical, real independence from Western-built engines. And now something important has quietly shifted. A specific set of three-dimensional printed components are no longer stuck in laboratory testing. They have officially been certified, and they are now being installed on serial production PD-14 engines rolling off the actual assembly line. So what does three-dimensional printing genuinely change inside this engine, and can it actually help Russia scale up both the PD-14 and the MC-21 program that depends on it? Let's walk through exactly what just changed. The component sitting at the center of this entire story is called a swirler, and on paper, its job sounds almost deceptively simple. It takes incoming fuel and air and forces them into a tightly controlled spinning motion inside the combustion chamber, the specific section of the engine where that fuel-air mixture gets continuously ignited during operation. Picture stirring cream into a cup of coffee. You create a swirl specifically to mix everything quickly and evenly throughout the liquid. A swirler does essentially the exact same job, except in this case, the coffee is burning at temperatures approaching 2,000 degrees Celsius. And that single detail changes absolutely everything about how difficult this part actually is to manufacture correctly. Get the internal geometry wrong by even a fraction of a millimeter, and the fuel-air mixture can start burning unevenly inside the chamber. Worse still, the flame itself can become genuinely unstable, and in the worst case, simply go out entirely mid-operation. So exactly like the opening of this story suggested, this was never really about squeezing out better thrust or efficiency numbers on a spec sheet. It was about whether engineers could physically manufacture the precise shape this particular part actually needs to be in the first place. So what exactly made this specific component so difficult to build to begin with? The swirler is manufactured from a nickel-cobalt superalloy called EP-648, an alloy specifically engineered to survive continuously inside an open flame without melting or deforming. Think of it as something like a specialty heat-resistant steel, similar in spirit to what gets used inside turbocharger housings, just pushed considerably further in terms of raw thermal performance. Here is the actual problem engineers ran into for years. Casting this specific alloy using the traditional method, pouring molten metal directly into a mold, kept failing consistently. EP-648's notably high chromium content forms brittle compounds as it cools down from a molten state. Picture pouring cake batter that keeps curdling before it ever has a chance to properly set, no matter how carefully or precisely you mix the ingredients beforehand. That was simply the frustrating manufacturing reality engineers faced for years on end. It wasn't that the process was merely slow, it was fundamentally broken as an approach for this specific alloy. That is exactly why three-dimensional printing matters so much here. Printing sidesteps this entire underlying problem completely, because nothing ever actually gets poured in the first place. A precisely controlled laser melts an incredibly thin layer of metal powder, thinner than a single sheet of paper, fusing that layer directly into the intended shape based purely on a digital design file. Then another layer gets added directly on top, then another. The part essentially grows into existence, layer by layer, rather than ever being poured into a mold or carved down from raw material. No pouring means no curdling. No curdling means no cracking. And this actually is not some brand new concept for Russian engineering either. Back in 2015, engineers at the United Engine Corporation's Aviadvigatel division teamed up with a specialized materials research institute called VIAM, specifically to design a printed version of this exact component. That early collaboration produced the very first Russian-made component ever successfully integrated into an actual operational jet engine using this specific printing method. So what genuinely changed in 2025 was not really the underlying technology itself. It was successfully moving that same technology out of a one-off engineering experiment and into something fully certified for genuine serial production at scale. And there is a real, measurable speed advantage that comes along as a side effect of this shift too. Early data on the process suggest roughly a tenfold speed improvement compared to traditional casting, with some reports describing a drop from around 60 days down to somewhere closer to just 6 days for producing a single finished part. That is genuinely the difference between waiting 2 full months for a replacement component to arrive versus having a fully finished certified replacement part ready before the following weekend is even over. So printing clearly solves the underlying cracking problem that plagued traditional casting for years. But does that actually translate into a meaningful benefit for the aircraft itself, beyond simply solving a manufacturing headache? It turns out the answer is genuinely yes, in a fairly direct and practical way. Traditional manufacturing typically starts with a large and solid block of raw metal, then systematically cuts away everything that isn't part of the final intended shape, essentially carving a finished statue out of a much larger boulder. Printing works in the exact opposite direction. It only adds material precisely where the actual design genuinely calls for it, and nowhere else. That means less wasted raw material overall, and meaningfully lighter finished components. And inside an actual airplane, every single gram of weight genuinely matters. Lighter individual components translate directly into better fuel efficiency across the entire aircraft over its operational lifetime. But being faster to produce and lighter in weight doesn't actually mean very much if you can't also definitively prove the resulting part is genuinely safe to fly. And this is exactly where the process gets considerably more serious. Every single printed swirler undergoes an inspection process that is honestly more rigorous in some respects than what many surgical implants go through before being approved for use in a human body. A three-dimensional optical scanner carefully checks the finished part's actual shape against the original digital blueprint, verifying accuracy down to fractions of a millimeter across the entire surface. Separate material tests confirm the finished metal genuinely behaves exactly the way EP648 alloy is specifically supposed to behave under stress and heat. Then, X-ray computed tomography scanning looks directly through the solid metal itself, hunting for any microscopic internal voids that could potentially develop into dangerous cracks once the part is subjected to sustained heat and vibration during real flight operation. And here is something genuinely worth understanding clearly. This is not some uniquely Russian manufacturing hurdle at all. Every single aerospace manufacturer on the planet runs directly into this exact same wall when attempting to certify printed components for critical hot section engine use. It is precisely why GE Aviation, despite having dramatically more resources and roughly a decade's worth of head start in this specific area, still took several years to successfully move three-dimensional printing from early prototype stage all the way through to genuine mass production certification. Successfully certifying a hot section engine part using this method is never some kind of manufacturing shortcut. It genuinely represents the single hardest regulatory and engineering gate in the entire aerospace certification process, and Russia's United Engine Corporation just successfully made it through that exact gate. But one single certified part is still, at the end of the day, just one part. So how far does this actual capability genuinely scale beyond this one specific component? The United Engine Corporation is not stopping with the PD-14 program. The company has already separately designed and built more than 2,300 distinct three-dimensional printed parts intended for the PD-35, a considerably larger engine program that currently remains in the demonstrator testing stage, and the exact same underlying manufacturing methods are simultaneously being applied to the PD-8, a smaller engine specifically designed for regional jet applications. So the honest answer to one of our opening questions here is genuinely yes. This manufacturing approach is actively starting to scale across multiple engine programs simultaneously. The overall goal here was never to fully replace traditional casting everywhere across every single component. It is specifically to use printing exactly where it genuinely earns its keep in terms of solving real manufacturing problems. So this particular technology is clearly scaling quickly within Russia's domestic aerospace industry. But how does that actual progress genuinely compare to where the rest of the world already stands on this same underlying technology? This is exactly where we need to be completely honest about relative scale, not to take anything away from what the United Engine Corporation just successfully accomplished, but because without this kind of direct comparison, the milestone itself doesn't really mean very much in complete isolation. GE Aviation actually started mass producing three-dimensional printed fuel nozzles for its LEAP engine, the exact engine currently powering the vast majority of Boeing 737 MAX and Airbus A320neo aircraft worldwide, all the way back in 2015, a full decade ago at this point. Each individual LEAP engine carries roughly 19 separate printed nozzles. GE has sold well over 16,000 of these engines to date. Multiply those two numbers together and you're genuinely talking about hundreds of thousands of individual printed components currently flying, having already accumulated more than 10 million cumulative flight hours in active commercial service. GE's newest engine program pushes that number even further still, incorporating somewhere around 300 separate printed parts within a single engine. Russia, by direct comparison, currently has exactly one certified printed part in genuine serial production, installed on an engine that has not yet even entered commercial passenger service at all. It is genuinely worth thinking about this, less as Russia suddenly catching up to where the West already stands, and more accurately, as Russia finally walking through a specific doorway that GE first walked through back in 2015. That particular door is genuinely difficult to open at all. Plenty of aerospace programs around the world have never actually managed to open it successfully. But walking through that door represents the very beginning of a much longer hallway, not the final destination itself. So with all of that context established, what about the actual MC-21 aircraft program itself? And this is precisely where the PD-14 engine's genuine manufacturing progress runs directly into the broader MC-21 program's current reality. The MC-21 program actually flew its first genuinely serially produced aircraft on August 3rd, 2026. That represents a real meaningful milestone in its own right. It specifically means the actual production line itself, not simply a prototype workshop, can now successfully build a fully complete aircraft from start to finish. For the purposes of today's story, though, here's the specific part that genuinely matters. Formal certification, the official regulatory process that actually clears a commercial aircraft to legally carry paying passengers, remains very much still ongoing and unresolved. Back in May 2026, Rostec's chief executive Sergei Chemezov told Russian President Vladimir Putin directly in a face-to-face meeting that certification and the very first customer deliveries would slip again, pushed back to sometime in 2027. That specific detail is not some unconfirmed rumor or leaked internal document. That is the actual man directly running the entire program stating this delay publicly himself. And to be genuinely clear, that kind of delay is not really any kind of scandal by industry standards. Major aircraft programs slip their schedules constantly, across every country that attempts them. Boeing's 787 Dreamliner program ran roughly 3 full years behind its original schedule. Airbus's A320neo military transport program went years over its original schedule and billions of dollars over its original budget. China's own C919 commercial airliner program took nearly a full decade longer to reach service than its original planned timeline suggested. Building an entirely new commercial airliner completely from scratch, especially one that simultaneously has to rebuild its entire domestic supply chain from essentially zero, ranks among the single hardest industrial engineering projects that exists anywhere on the planet today. So, if virtually every major aircraft program eventually slips its schedule to some degree, how does Russia's specific version of this broader struggle genuinely compare against, say, China's parallel effort in this exact same space? This happens to be exactly the kind of direct comparison almost nobody actually makes, precisely because it cuts directly against the narrative most casual observers might otherwise expect going in. China's C919, easily the aircraft most directly comparable to Russia's MC-21 in terms of size and market positioning, is, as of right now, still flying entirely on Western-built engines, specifically the CFM LEAP-1C, built through the exact same GE and Safran joint venture partnership referenced earlier in this story. China's own domestic engine replacement, the CJ1000A, remains currently in active flight testing, with certification expected sometime around 2027 and genuine commercial service not realistically projected until roughly 2030, putting that program nearly 8 full years behind its own original planned schedule. So here's the genuine paradox sitting right at the center of this entire comparison. China's overall aircraft program is, in many meaningful respects, considerably further ahead than Russia's, with more aircraft actually delivered to customers, more confirmed orders on the books, and dramatically more established manufacturing scale overall. But its engine remains entirely Western in origin. Russia's aircraft program, by direct contrast, remains genuinely behind China's on most of those same metrics, but its actual engine is already 100% domestically produced and is already flying real test flights right now, today. Which specific program actually counts as more genuinely independent depends entirely on exactly which metric you personally choose to prioritize when measuring it. Count total delivered airplanes, and China is clearly ahead by a wide margin. Count genuine freedom from a Western supply chain that could theoretically be shut off entirely through a simple export license restriction, and Russia is actually considerably further along, at least specifically regarding the engine itself. Both of those seemingly contradictory statements happen to be genuinely true at the exact same time. Neither one actually cancels the other one out. So here is the honest, complete summary of where things genuinely stand. What has genuinely changed inside the PD-14 engine program is real, a genuine manufacturing problem that has now been fully solved, properly certified, and is already actively scaling across 2 additional separate engine programs simultaneously. What hasn't genuinely changed yet is the MC-21 aircraft program itself, which remains a year or more away from actually carrying its first paying passenger. In a very real sense, the engine program has gotten meaningfully ahead of the airplane program it's actually meant to power. And when you place that specific situation directly alongside China's own parallel version of this exact same broader struggle, it turns out that determining who is genuinely winning this particular race depends entirely on which specific finish line you happen to be watching most closely.